Hi, my name is Mohammed, and this is the Teach to Learn assignment number 1 on process synchronization. Basically, we've heard of the who stole two counts from me problem. And so basically, this was a simple program that just had multiple threads that shared a string buffer, reading and writing, all like to reach 5,000. Okay, so we had a thread that was adding, a thread that was taking, and we have the problem is that we don't have exactly 5,000. Now, why is that? Well, the problem is because of a race condition. Okay, so a race condition happens when the outcome of execution depends on the particular order. So basically, you don't know what happens in a clock cycle. So in a producer-consumer problem, you could actually be trying to consume products of an array that don't exist because you interrupted a process that was adding, okay? So that's why we say that the execution depends on the order very much strongly, okay? So the synchronization problem is that whenever we have concurrent access, we have data inconsistency, okay? So here's the problem, okay, in code-wise form, okay? So this is the producer consumer problem. So this is the producer code. And so basically it just tries to wait, okay? So here it produces an item and adds it, okay? So here it waits if the list is full. So it waits for the consumer to just remove it, and realize that the while has just a semicolon here. And then to produce an item, it just um, takes a variable called in, which is updated here. Okay, and of course it's modulus by the buffer size because you don't want to go out. It's like a circular queue in some sense, and then you want to put it in and then make an item and put it there, and then the counter. So this shouldn't be counter. This should be count. Okay, and so basically, this is kind of like an infinite while loop that keeps doing these to add items. Okay, and this is the race condition that basically just goes out with the items. So if there's no items, it waits. Okay, and then the item equals buffer of out. Okay, and then it adds out so that so imagine an array with me here, and it's trying to remove items from it. And then the counter is removed. And buffer is the array that we are working with. And then here you have consume the item, which is basically to just remove that item from my array. Okay. So basically, in order to imagine that, we just go to making an array. And producer would basically just keep adding items. And then the consumer would just keep taking these items. And as long as, if we have 0, for example, you can't keep taking items. So, Mohammed, where does the problem happen exactly? Well, the problem happens if you're trying to add an item, okay? And then as you're adding, like, so let's say you have A, B, C, D, and then you're adding E. You're trying to add E, but before you do that, the consumer interrupts you and takes D. Okay, and so you did not just add E, you did not add E, but you did not add D. So, well, what's the problem exactly? Well, your count is different now. Your buffer is different now. And so this is when the race condition happened. Okay, so now we are going to go back to our slides. Okay, so now we go to a solution. Okay, and it is the critical section problem. Okay, so what we're going to do is we are going to say, what's exactly critical for a process, for a thread of the process to go through. Okay, so we put that here, and then we're going to lock it. Okay, and we're going to call that entry section. Okay, so basically, in order to add an item to your array, remember that you have like 3 steps approximately, is to load that item into memory and then to put it there. And so what you need to do is you need to make that process atomic so that nothing can interrupt it. Okay, that's what it means. So what we're going to do for the last thing today is take a look into Peterson's solution. So keep in mind that Peter's solution has limitations. It's strict and only between 2 processes, and it only like ambiates between them. So it's 1, 2, 1, 2. You cannot say 1, 2, and then you say 2. No, you have to switch on to the other one. Okay. So how does this solution work? Okay. Well, that's a very good question. So I'm annotating here. So so as you can see, the it starts with a while loop, okay, here and there, and it has, so remember that this is going to be the code for both 2 processes together, working together, okay, and it's going to say flag of I is true. So what is flag? So flag is an array, okay, and it indicates, and this part indicates whether you are a process that wants to enter the critical section. Okay, so which is to add or remove something. Okay, so if it's true, that means you want to. Okay, so you have a need to actually get in there, and if it's false, you don't need to. Okay, and turn equal j basically is still variable, meaning that it just uh, doesn't get changed in the process, but gets changed by the other process. Okay, so turn equals j means that the other process is the process that that is already in. Okay, so assuming that turn equals j, okay, you will here have a true condition for this while loop. Okay, so you say flag of I equals true. So j is the other process. Okay, so the other process wants to get in, and it's actually the turn of the other process. So you get stuck into this while loop because it has no body, and you wait for it to finish. So how does it finish? So remember that this code is in the same other process as well. So you have flag of I is also flag of j. Okay, so if flag of j is set to false, it's going to update here and going to break that while loop. Okay, so what does flag of j mean? It means that the other process no longer wants to enter its critical section because it already did, because it's outside of here. So the other process goes into the critical section. And then it sets to false, and then the remainder section, which isn't really critical. And so how do you put code into the critical section? Well, you see, what's the code that has a race condition risk, and you put it there. Okay, so just don't throw all of your code into the critical section. Okay, thank you very much.